There are a few scientific principles we need to understand before we can get into the full explanation. In the first part of this video, we'll explore these principles, laying the groundwork for understanding how a heat pump operates. Then in the second part, we'll integrate these principles to provide a comprehensive overview of the heat pump's functionality. Let's begin with the first part and the scientific principles. Number 1. A heat pump transfers heat from one location to another using a refrigerant and a thermodynamic process called vapor compression cycle. Number 2. Heat naturally moves from areas of higher temperature to those of lower temperature. The speed of this heat transfer depends on the temperature difference between the two regions. The greater the difference, the bigger the transfer. Heat always passes from hot to cold. 3. Available heat in the atmosphere is strangely different to how we think about it in our normal lives. Ignore for a moment the concept of what feels hot or cold to us and think of heat as an energy we are trying to take from the surrounding atmosphere. The Kelvin temperature scale is used by scientists, where 0 reflects the complete absence of thermal energy. This is different to the 0 degrees C we normally think of as freezing or water forming into ice. In the Kelvin scale, absolute 0 is minus 273 degrees C, as you can see on the comparison scale. The important part to draw from this is, whilst we might perceive 3 degrees C, for example, as cold or near freezing, and whilst that is true in terms of what we feel, there is still available energy within the atmosphere that can be absorbed by refrigerant that is used in the vapor compression cycle. Number 4. When a refrigerant changes state from a liquid to a gas, it absorbs a large amount of thermal energy. This process is called vaporization. Number 5. When a refrigerant changes state from a gas to a liquid, it releases a large amount of thermal energy. This process is called condensing. Number 6. If we compress a gas, it increases in temperature. Increased pressure equals increased temperature. Number 7. The boiling point of a liquid depends on its pressure. Water, for example, boils at 100 degrees C under normal atmospheric pressure, considered to be 1 bar at sea level. At higher altitudes, air pressure is reduced. As an example, Mount Everest has a pressure of 0.3 bar, which allows water to boil at 68 degrees C. Two gas laws which help explain the vapor compression cycle are Boyle's law and Charles' law. Boyle's law states that when you increase the pressure on a gas, its volume decreases, and when you decrease the pressure, its volume increases. To make that easier, think of a balloon. If you squeeze the balloon, its size will shrink, but if you release the pressure, it will expand again. This illustrates how pressure affects the volume of a gas. Charles' law states that when you increase the temperature of a gas, its pressure increases, and when you decrease the temperature, its pressure decreases. Think of a balloon left out in the sun on a hot day. As the temperature rises, the air pressure increases inside the balloon, causing it to inflate. If you were to place the balloon in a cold environment, the air pressure inside would decrease, causing the balloon to deflate. This illustrates how temperature affects the pressure of a gas. So, how is all of this relevant to a heat pump? This manipulation and control of pressure exerted on the refrigerant in the vapor compression cycle is fundamental to the operation of a heat pump. A heat pump manipulates a refrigerant to create heat in a highly efficient manner. That's already a large amount of information to take in. Feel free to pause or rewind the video if you need to and recap the scientific principles we have listed. We will now move on to the second part of the video, delving into how these scientific principles come together to make a heat pump function. It is easier to understand if we divide the vapor compression cycle into 4 stages, each corresponding to the relevant part within the heat pump. These 4 stages and their corresponding parts are: number 1, evaporation at the evaporator; number 2, compression at the compressor; 3, condensing at the condenser, and 4, expansion at the expansion valve. We will start at the evaporator. At this stage of the vapour compression cycle, the refrigerant in the evaporator is at a far lower temperature than the surrounding outside air. It is also on the suction line into the compressor, which helps maintain a low pressure. Remembering that lower pressure reduces the boiling point of a liquid, and heat moves from area of higher temperature to areas of lower temperature. The greater the difference, the bigger the transfer. We have an evaporator filled with a very cold, low pressure refrigerant, having warmer outside air pulled over it by the heat pump's fan. The heat energy in the air is being absorbed into the refrigerant, causing it to boil, changing its state from a liquid to a gas. The liquid is evaporating into a gas, also known as vaporization. It's important to note here, the temperature of the refrigerant is still relatively low as it leaves the evaporator, but it has absorbed heat energy. The next stage is the compressor. The low temperature, low pressure vaporized refrigerant now enters the compressor via the suction line. The suction line connects the evaporator to the compressor. Remembering that an increase in pressure resulting in a reduced volume of gas increases its temperature. The vapour is now compressed and squashed by the compressor, reducing its volume and significantly increasing the temperature in the process. The compressor is the main part that uses electric to work. We now have a high temperature, high pressure vapour leaving the compressor. The next stage is the condenser. The high pressure, high temperature vapour enters the condenser via the discharge line. The discharge line connects the compressor to the condenser. Remembering that heat moves from areas of higher temperature to areas of lower temperature, the greater the difference, the bigger the transfer, and when we cool a vapour down, it condenses, changing state from a gas to a liquid, releasing or rejecting the heat energy it has absorbed. We now have a condenser, which is essentially a heat exchanger. It has a high temperature, high pressure vapour passing through one side, with cooler central heating water passing the opposite way in the other side. As the vapour starts to transfer its heat into the central heating water, it begins to condense. Once it changes state from a vapour to a liquid, it will have released all the heat energy it previously absorbed into the central heating water, which will go around the heating system's pipes and radiators within the house, assisted by a circulator pump. We now have a relatively low temperature, high pressure liquid leaving the condenser. The next stage is the expansion valve. The relatively low temperature, high pressure liquid enters the expansion valve via the liquid line. The liquid line connects the condenser to the expansion valve. Remembering that an increase in volume reduces pressure and significantly reduces temperature. We now have a high pressure, relatively low temperature liquid entering the expansion valve. The valve quickly allows for the expansion of the liquid, decreasing its pressure and significantly decreasing its temperature. This refrigerant is back to a very cold, low pressure state where it enters the evaporator via the vapour line to absorb the heat energy from the outside air. The vapour line connects the expansion valve to the evaporator. Although on first viewing there seems a lot of information involved in how a heat pump works, rewatching this video will help embed the process. The vapour compression cycle is a continuous loop. The refrigerant circulates through 4 main components: the evaporator, compressor, condenser and the expansion valve in a continuous manner, transferring heat from one location to another through manipulation of pressure. The cycle repeats for as long as the heat pump is in operation. This process involves using units of electricity to drive the compressor, which manipulates the pressure across the vapour compression cycle. It utilises the heat energy from the outdoor air and a refrigerant as the medium for transfer, resulting in an increased output unit of heat. This makes it a very efficient method of heating our homes and water.